Today we're kind of beginning the machine learning part of this class. I've learned just a tiny bit. We're going to return to it to learn it in more detail, but just conceptually we learned about, what forms an image is the radiation in the real world, some real world wave-like phenomena, typically a measurement device. We can model that as a black box, right? Which reduces to a convolution type modification to the representation of the radiation as a wave. Those can be cascaded in a series of black box operations. So a series of convolutions effectively. Those lead to our detector. Those are kind of known things we need to generally have knowledge of to model how the picture is captured or understand how that whole process works. And then the detector captures the signal and digitizes it, right? And as long as we sample effectively following the Nyquist-Shannon sampling theorem, then we can fully recreate the wave that hit the sensor, right? From the discrete number of measurements that we capture. So that forms generally a 1D array of numbers or a 2D array of numbers that enters machine learning. And so that's what we'll talk about today. And machine learning, I'm kind of using a general term. Today, I'll talk about optimization, which is, I guess, a parent category a bit for machine learning methods. The data is then processed by a computer to then give something useful as the output. So yeah, this will be then sort of a review or a framework of optimization that we'll then use for the rest of the course. Okay, so mathematical optimization really is the selection of a best element with regard to some criterion from a set of available alternatives, right? So really optimization is about finding an answer, right, which is quote unquote this best element. You need to return something, one thing generally, and you have a set of alternatives. So you have a set of things you're considering as the answer, and you want to find the right one. And so how do you find the right one? Well, you need some criteria. You need a way to say, hey, this one's better than that one. This one's really good, but not quite the best, right? And then here's the best one, right? So that's really what we're after in optimization. So there's a kind of breakdown of those three elements, and there's really three things you need to really, well, kind of four, but three main things you need to think about in optimization. So the first, this best element is your output, right? You have some optimization process. You're going to hit enter on your computer. The computer is going to do something, right, from your eyes, and then you get something out, right? So the output is what you want. It can be very abstract, right, of course, but in this class, we're talking about images and image analysis, right? So the output can be an image. Give me a better image of this, or clear up this image, or, give me that, but, modified so that the colors do this or whatever. 3D shape is highlighted. It can be just a signal, more abstract signal. So before the image is actually formed, let's say in an ultrasound system, you want to clean up the wavefront coming. It can be a final answer, right? And so really what we're focused on is this last one. The output of most of our optimizations isn't, well, sometimes is an image, but it can be like, what is this image of? And then the answer is a cat or a dog, right? So it's in this abstract space, then that's your output. So the second element is a model. We need some sort of model to describe what we're trying to do. And I'll get more into that in detail. And so that model takes something and gives you your output, right? Tries to clean up the image. It tries to clean up the ultrasound signal. It tries to guess if it's a cat or dog, right? That's really what we're trying to get good at, is making those models class. And then the last thing is some criteria. And so in optimization and in machine learning, the criterion is very well defined. It's not so abstract. The other two things are like, could be this, could be that, and we'll see some examples. For machine learning and for optimization in general, this criterion is called a cost function. It's an equation. It tells you how good you're doing. The output of a cost function is a single scalar number. It just is, what's my score? How good is that answer? Criterion is equally as important as the others, and you should just get really comfortable with that fact that it's some measure of success. Okay, and so we're going to rely on pictures like this for the next few weeks, this kind of model I'll set up. And so you'll see this a lot, and it's kind of drawn from right to left, like backwards, because that's the way when you write out the math, it mirrors this format. right? And so we're going to start in optimization and in machine learning with some input, right? You need to give the computer something or the optimization process something to work with. So our input is generally imagery, right? Because that's what we capture and want to analyze. So here's an image of something, right? You can't quite tell, A, because the projector is kind of dark, but B, I added a lot of noise to this image. That's our input, and we're going to have the input in our heads and all of our equations that we're going to write in this class is going to be a vector, right? So a column vector. The input dimension is something like n squared, in this case, where n is the number of pixels, n's probably like 400, I guess, in this case. So the dimensionality of this space going into our model is 400 squared. That's our input. And then the model does its thing, right? There's many models, and we're just going to consider it abstractly right now. Just think of it as some gears, churning those numbers, doing something. You get an output. The output's a vector, and that has a dimensionality. The output is what we want, right? It's a better image. It's some categorization of what is in that image, some process of drawing a segmentation boundary around where the cat or dog might be, etc. That has a dimensionality m. And then we need to apply our cost function to say, how good are we doing at this process of getting what we want? How good was that guess of cat or dog? Or how good a job did we clean up the noise in the image? That cost function is going to reduce our output dimensions m, an m long vector, into one number, a scalar. We're not going to discuss this in this class, but we're going to leave this arrow out. But in machine learning, what we do is we try to use that cost function to find a really good model, right? So I'm just going to throw that out there right now. So we're not going to include this arrow today, but in machine learning, the whole goal is to take this model and alter it, try to create a better artificial intelligence algorithm to determine if this is a cat or dog or whatever the case may be. That's our whole thing. Just consider this abstract problem. First, we have to understand how to do this part before we add that arrow in. All right, and so this part without that arrow is optimization, right? And so I'll show you a couple very simple examples of optimization. So what's the closest image to what I detected, except without so much noise, without so much fluctuations? That can be one optimization goal, right? And so let's lay that out. Our input dimensions are n by n image. It's that 400 by 400 pixel image of that kind of cat dog example thing. I don't even remember if it's a cat or a dog. Our input dimensions n by n are output dimensions the same as our input dimension in this example. It's also an image, right, that just has less noise. So then that goes into our model. Our model is going to then try to find a better image that's less noisy, has less fluctuations. So our cost function is going to try to, it's something we decide, right? This whole process is something we have to assign to the computer to do. And so a good cost function in the case of denoising, removing noise, is going to say, hey, neighboring pixels shouldn't fluctuate so much. They should kind of be the same, right? If I take a picture of this room, most of the pixels next to each other are sort of similar. Like that wall back there is all gray, that's all white. Your shirts are generally not speckle noise, they're kind of uniformly colored. And so neighboring pixels should relatively be the same, and then that'll reduce the fluctuations from pixel to pixel. And so the cost function for that looks like this. Pixel 1 and pixel 2, if they have a similar value, the cost function is low. So something else to remember is we always want to have the cost function be as small a number as possible. So when the cost function goes down, we're in good shape. That's just like a nomenclature. I don't know why, but that's what the optimization community has decided, is minimizing the cost function is our goal. So smaller is better. Just keep that in mind. So if the cost function outputs something close to 0, or rather if we choose an answer where pixel 1 and pixel 2 are similar, meaning, under our assumptions, implying that there should be less noise, then the cost function is going to give us a lower number. We're doing good. And if pixel 1 and pixel 2, the neighboring pixels, are dissimilar, right? Pixel 2 is like 1, and then pixel 1 is close to 0. That's probably not a good choice, right? Because that's a noisy image. And so I'm drawing 2 dimensions here, but our cost function is going to operate across a 400 by 400 dimensional space, right? So I can't draw 400 square dimensions. I can't draw more than 3 dimensions, right? So you have to abstract this picture to 400 square dimensions, but it's the same idea. Okay, so we apply this cost function, and then we can get ideally a smoother image, let's say, an image without as much noise. So what does that look like in terms of how optimization works? Well, the way optimization works generally is we say, we're going to start with a guess. So we want a less noisy image of this dog. And so our guess probably is going to be the original image with noise, right? Maybe we do a little pre-filtering and try to remove some high and low pixel values or something. And that's going to be our guess. It's going to fall onto this cost function at some point, right? Again, I'm just showing 2 dimensions. It's going to fall. It's going to be a point in this 400 square dimensional space, right? And that's our original guess. And what optimization does is it simply minimizes the value of the cost function. How does it do that? Well, we'll learn about that. But in essence, you just go down the hill, so to speak. And so in optimization, the computer is instructed to just look for the direction of most change going downwards generally, or just some direction where you're going to go downwards and minimize the cost function. Take a step down that hill and then check how good did I do, and then take another step down the hill, et cetera, et cetera. Each time it'll modify its direction to try to walk its way down the hill to the bottom, just as you would if you were on a mountain and there was lots of kind of rocks and stuff, and you had to work your way to the bottom, right? And each time you're doing that, you're taking a step, and you're not like looking way out 100 yards ahead all the time. You're generally just kind of looking one step at a time, and you're going down, right? So that's really what the computer does. It looks just one step at a time and says, okay, it's a little bit steeper over there, and okay, I'll go that way, and then that way, and that way. And in some circumstances, in machine learning, generally, this isn't true. Some circumstances, these cost functions are designed to have a single minimizer, so a single valley. And so the computer almost always can find the minimum value, right? And so computers, just as a, shouldn't come as a surprise, but computers are really good at that process. This step going downwards the hill iteratively process. And so that process will go down the hill, and then ideally we get this denoised image out. This is, again, kind of hypothetical. Okay, so that's this one form of model where the input here is the same size as our output. But that cost function, remember, it's a function right in that space, so it has a scalar value at any location in that space. And so when we evaluate that function I drew, we always get out of scale. So that's important. That you have to satisfy that criterion in optimization and machine learning. So here's a second example that's a bit more abstract. So now our model, let's say, is some magical function that some person made that takes an image in and just tells you if the image is a cat or a dog. And so generally humans don't make these magical functions, machines do now, but just bear with me here. This is an abstract example a bit. So we have an input image. Again, the image has 400 by 400 pixels. It's going to go through our model, this magical model. It's some very, very long set of equations. We get an output. The output is a vector of 2 dimensions. One dimension is what percentage chance is that image of a cat, and the other is what percentage chance is it of a dog. So now our dimensionality that we're working in, I can draw, and it looks something like this, right? Where on the one axis coming out, it's percent chance cat, the other it's percent chance dog. And so in this space, right, what are we going to do to solve this optimization problem? And I'll also note that I just took the MATLAB symbol actually to make this function. It's some nonlinear function, right? It is probably a very complicated function, but someone did their best to develop it. So now how do we solve this? Well, we do the same thing. We start with a guess, and here our guess is probably, well, I don't know. I have no idea. So I'm going to put my starting point right in the middle of this 2-dimensional space. I'll say it's 50% chance cat, 50% chance dog, something like that. And then we're going to go down the hill, so to speak, and try to find the answer. You'll note here that I could have gone, or the computer could go down the hill and end up in this valley or this valley. It depends how it decided to go down the hill. This is a problem in general with nonlinear optimization. You arrive at answers and it might not be the correct answer, right? You have no guarantees that you'll get to the actual correct answer, assuming your model was set up correctly. And so every machine learning problem really in practice is nonlinear. There's 0 guarantees that you're actually getting the right answer. Okay, so just keep that in mind. So this picture is relevant, and it's actually in a much higher dimensional space. These rapidly fluctuating functions, the cost functions really, that have tons of little valleys, millions and trillions of little valleys. Okay, and so in this case, our input dimension was very large compared to our output dimension, 400 squared, and then 2. But again, we had to have a cost function that reduces those two numbers to a single scalar value, right? Telling us how well are we doing. To present optimization, I'm going to go through this example that I like because it's easy to describe mathematically. You'll see it's actually not that easy, but compared to all other optimization problems, it's the easiest convex optimization problem that I can muster that actually is mildly relevant. And it has a lot of additional features that take the problem from a standard convex optimization problem to a more complex one, okay? And so for that reason, I like to go through it. And also when I get confused about optimization, I kind of revert to this example in my head or even on paper to work things out. I'm like, wait, what, or I'm reading a paper and they do something crazy. And I'm like, how does that really work? And I come back to this because I fully generally understand this, because optimization gets pretty complicated. Okay, and so this is, if you become comfortable with it, a good anchoring problem to think about. Okay. And also I work in optics and it's an optical problem. So I'm a little bit biased there. But it's relevant to this class because we're talking about data capture abstractly, images in particular, and working with that data to get some answer. Okay, and so the problem that I'm going to describe is called spectral unmixing. That's a pretty broad term. This is like the literal problem of spectral unmixing. People use the term spectral unmixing also in other fields that don't really deal with spectra of light or radiation. So this problem generally has applications in other spaces as well. Spectral unmixing, I mean, there's a variety of ways to think about it. I'll present one way to think about it, a simple way. So in spectral unmixing, you have some sample or something of interest you're trying to understand, right? Here I'll say that in a microscope or some small microscopic type sample, and that sample consists of a mix of colors, literally. And the goal of spectral unmixing is to figure out what percent of which color is in the sample, right? So it's really like you have a bunch of mixed paints and you're trying to decipher, well, what percent of paint A, what percent of paint B, what percent of paint C is in that mixture. In this case, I'll kind of present it maybe from a microscopic perspective. So here we have different fluorophores in some cells, right? Because I think a lot of you are BME majors, you should know about this. So you can fluorescently label specimens. It's done all the time in the clinic, hundreds of times a day at Duke Clinic. They'll put down fluorescent labels on different tissue specimens or cytology or blood smears and try to understand what's in them. There's only a subset of, you did the preparation of the sample, right? So you know what fluorescent dyes you put down, and you only put down so many. And then the goal is, well, how much of each is present, right? Because they attach to certain specific things of interest, and so you want to understand their concentrations. And so to do that, one could use a spectrometer. So a spectrometer is just, it takes all the light coming out of the sample, spreads it out into a rainbow, and measures the constituent colors across different wavelengths that are comprised, right, across the rainbow. And so the output of the spectrometer is a vector. It's a sequence of measurements, each measurement representing the amount of light detected for a particular color. Okay, so let's go through these 3 elements optimization. So what's our desired output in this spectral unmixing problem? Percentage of each color, percentage of each fluorophore. So we're going to say there's 9 different fluorophores in this problem. Why 9? I just made that up. It could be whatever, but that's a believable number of fluorophores that one might use to probe their sample, just to be concrete about these. Okay, so the output is what percentage of each of the 9 fluorophores are in the sample, right? It's a set of 9 numbers or a vector of dimension 9. So what's our model? The model, as I'll show, is something called a dictionary. It's a matrix that's going to allow us to connect our measurements to the percentages, the 9 percentages of interest. So I'll explain the dictionary matrix in a second. And what's a good cost function to use? So when in doubt, subtract things and square them. That's called the mean squared error. So if you ever have any doubts in machine learning or optimization, pick mean squared error as your cost function. Can't go wrong. Okay, so we're going to use mean squared error because it just works. There's better cost functions for specific problems, but then things get more complicated. So we're not going to do that. Okay, and so we have our three elements. We're pretty good, right? Number 2 is a little hazy. I'll show it in a second. But we have what we need to do optimization, right? That's it. So we can draw this picture now. So our input, it's going to be our measurements. It's going to be generally images in this class, but here it's a one-dimensional vector of measured brightnesses of each color. It has n entries, and I don't know what I end up picking. It's on the order of like a couple hundred pixels, right? So you generally split up a rainbow of colors with a grading, and then you have a couple hundred pixels to detect each wavelength. That goes into our model. The model I just told you is a dictionary matrix. It's going to map this n long vector into 9 percentages of each color. And then we have our cost function. We're going to take that vector of 9 possible percentages and look at it and then check how well we're doing. All right, that's the goal. What's this dictionary matrix? We can make it. So again, we're the experimentalists here. We have the spectrometer. We put the 9 fluorophores on the tissue specimens that we're looking at. And so before we do any of that, we're going to say, we need to make our dictionary matrix. So to make our dictionary matrix, we can take each fluorophore individually and measure its spectrum, right? Because we know that those spectrums are going to compose the mixture that we're going to eventually measure. And so we know our final signal is going to be composed of 9 individual spectra. So we want to measure those 9 individual different color bands, right? Each caused by each fluorophore. So we can take one fluorophore, let's say a blue one. Pacific blue is a popular fluorescent label. And we'll put it under our spectrometer and we'll measure something like this. So here, spectrometers go from lower wavelengths to higher wavelengths. So blue is towards a lower wavelength. And so we'll detect a lot of blue for Pacific blue, but it probably has some tails, right? They're not just so sharp. They generally have a broad spectrum, especially blue ones. Okay, so we're going to take that set of measured n pixel values. Let's say n is 200. I'm just going to say that right now, even though I'm probably wrong. We'll see a different number on a later slide. But for now, let's say there's 200 pixels in our spectrometer. We'll put that as the first column of our dictionary matrix. So our dictionary matrix will have 200 rows. And how many columns do you think our dictionary matrix? 9. That's right. Because it needs to map, right, 200 dimensional to 9 dimensional. So then we'll put down our next fluorophore. Let's say it's GFP, green fluorescent protein. That's everywhere, right? That's the one that won the Nobel Prize and got everyone interested in fluorophores. So it's probably good to use that. We'll put that in and we get a greener measurement, right? It's shifted from blue to green, it's the curve. And we'll take that and put all of those values in our second column. And we'll repeat that process. So we have 9 different colored fluorophores. Now we have 9 full columns. And our 200 row by 9 column matrix A is now populated. So from our discussion a couple classes ago of how to think about matrix multiplication, we know that matrix multiplication can be thought of as a linear combination of the columns of the matrix, right? And so naturally, your kind of a bell should be going off and saying, hey, we have this matrix of all the possible colors. We're going to mix them, or they're going to be mixed, and then we want to measure it. And so that'll somehow add up all those columns, right, to produce our measurement. And so we're going to probably want to do a matrix multiplication with this dictionary matrix. Okay, and so that's exactly what we want to do. Now we can start to put our problem together. We have our unknown sample percentages as 9 values. We can make those a vector, right? We've already kind of considered that. It has 9 values in it. And we can multiply those 9 values. Each one's a weight. So I'm going to introduce this term weight here. We're going to talk a lot about weights in this class. Weights are things that we want to figure out in this class. And so here we have 9 weights that we don't know, right? This is what we're trying to figure out. And so y is right now just some array that we can put random values in that maybe we think are good guesses. It could be evenly distributed. So each one could be 0.11 on. So then they'll add up to 100%. And then that assumes all the colors are evenly mixed in the sample or whatever it is, right? It's really up to us. And then we perform a multiplication, right? And so when we multiply y into a, the result will be literally that linear combination I just mentioned. It'll be the first value of y times the first column of our dictionary matrix plus the second value of y times the second column, et cetera, et cetera. Okay, and so that's going to lead to our new measurement. So if we put a new sample under our spectrometer and it has an unknown mixture of different percentages of each fluorophore, we can model that as the matrix products of y into a, which then equals our new measurement x. We don't know the values of y yet, right? But that's what we're trying to figure out. If we did know the values of y, then we could multiply those known values into a, and they should match our measurement x, right? In this new scenario. Okay, and so you can write in a matrix equation, x, your measurement equals the dictionary matrix A times these unknown weights y. So our goal in this optimization problem is given A, right? A is something we can measure, right? We just put each fluorophore one under a time. We can like save it for, it's not going to change that much week to week. We know X, that's what we measure, right? We capture and we get these 200 numbers out of our spectrometer. And our goal is to find Y. That's our optimization. Okay, and so just as an aside, as we get more and more into machine learning, this dictionary matrix here, we know it, right? We have some ability to gain information about the experiment. If we didn't have A, we'd be screwed, right? There's nothing you can do. And for very little you can do, right? Here's a measurement. What percentage of the fluorophores, what possible colors are you considering? Like what mixtures of fluorophores are there? It's a really hard problem. And so once we get into machine learning, we're going to need to use some knowledge or information about the problem we're trying to tackle, some real world input to help us. And that's called training data, right? So you can't do machine learning type work for free. You need some insight, you need data. So in this problem, the data we have is not so much, it's just 9 measurements, right? That's enough to really get us going. In machine learning, we need like hundreds or thousands of training examples, measurements that we can acquire to help achieve these optimization processes, right? So I just want everyone to remember that. You can't just do machine learning for free without data. And if you can download some algorithms that work. Just realize that other people have taken lots and lots of data to make that already. And so if there's a mismatch between the data that's been used to make a machine learning algorithm and the data that you're capturing, there's going to be a problem. Just like if there was a dictionary matrix A that you captured on one system, and then someone's using a different set of fluorophores and they try to use your same dictionary matrix, it's not going to work well, right? So you really need to know these kind of parameters and how they impact what you're trying to do. All right, cool. So we're going to try and solve this problem. Okay, so our cost function now, we can write it out. We're going to use this mean squared error metric, y. And the reason why is because of noise, right? Any measurement has noise. And so we can't directly write every single time we put down a sample and we get a measurement x, we can't say this is exactly equal. There's always some noise value. And here we're going to say it's like additive noise, for example. The spectrometer has some electronic noise and the pixels can fluctuate a little bit, right, for example. But there's all sorts of other noise. The fluorophores get old, their spectrum change a little, right? There's all these parameters. Here we're going to sweep those under the rug. We just are going to model our system as a linear equation with additive noise. When you have that type of problem, the mean squared error is the optimal cost function to use to solve the problem. as we'll see. We can just directly write the cost function as a function f, right, which sums up the square difference between our measurements x and the product ay. And so here, what this equation is saying is we're going to compare our measurements that we actually took to the product of some guessed percentages y into our measurement matrix A. So again, whenever you do this kind of cost function, you're comparing two things, right? You need to work with what you have. And so in this problem, what we have are our measurements. We measured some spectrum. So we're going to compare that to some model, right? And what are we going to model? Well, we'll model a spectrum. And we'll just guess what force caused that spectrum. And hopefully we're going to guess good, and the two will be close to each other, what we measured and what we're trying to predict. And if not, then we need to change the values in y, change our guess percentages to get that match closer. And that's the whole goal of our optimization. Okay, and so that now we can write the whole thing mathematically. So we have our inputs, our measurements, our model, and our outputs y, and then our cost function, right? We can actually draw a picture of our cost, right? And so here again, what dimensionality are we working in for our cost function? How many dimensions are these axes in reality? 9, that's right. Can't draw 9 dimensions. Well, you have to draw 10, so you have to draw the y-axis too, always, which is the actual value of the cost function. And I can't draw 10 dimensions. So here's just 2, y1 and y2. But mean squared error is something squared, right? So it's a parabola in 1 dimension, and then it's a paraboloid in 2 dimensions. And so it's some 9-dimensional paraboloid that we are using to help us find the best value of y. And so the optimal solution in this problem has an optimal solution by construction because it's actually a convex problem. There's a single minimum, or a single minimizer rather, y star, that is the location of the bottom of this parabola. Our goal is to go down the paraboloid until we get to the bottom. That's the solution. And so we start with a guess and we go down. That's one approach to solve this problem with the computer. Okay, and so how do we go down the hill? Well, when you go down the hill, you need to know the slope, right? Or it's good to know the slope when you're trying to go down the hill. If you don't know the slope is lower that way and higher that way, then you could just end up going up the hill, right? And so we want to measure the slope, and so that mathematically means we're going to evaluate the derivative of this cost function. And we're going to evaluate the derivative, and it's not going to be a 1-dimensional derivative. It's a 9-dimensional derivative, right? Because we're in a 9-dimensional space. And so that's a vector derivative. And so we want to figure that out. So let's go ahead and take the vector derivative of our cost function. So that's this, I'm using a bold symbol for y, d dy of the cost function f of y equals dy times the sum of those squared values of the difference between our measurements x and a times 1. And so the derivative can go inside the sum. And so now we need to just evaluate the matrix derivative of x minus ay, right, with respect to y. And so this isn't so hard. Again, it's this like matrix vector derivative stuff that is always confusing, but it's kind of the same as a scalar derivative. And so you can look at this and say, hey, well, the scalar derivative of x minus ay squared, well, that's probably like 2 times what's in the parentheses, 2 times x minus ay, and then probably times a, right? Because a, just like if a was a scalar, it just, you'd have that, what's it called? Like, I forget the term, chain rule type derivative thing you have to do. It might have been a while for some of you with derivatives, but just go back to high school books and you'll see that chain rule thing. Okay, and so the way it actually works out, because it's a vector derivative, you don't pull out the whole negative a yet. You kind of want to do it carefully. If you consider just the jth value of the vector y and take the derivative with respect to the jth value, you'll realize that what you need to do is consider the jth row of a as what you pull out. And so that means, just that's a long way to say that it's not actually a, it's a transpose, right? And so the vector derivative of that expression is equal to negative 2A transpose times x minus AY. If you don't believe me, you can spend a couple minutes trying to work it out. Another way to realize this is this dimensionality argument I told you about a couple classes ago about matrix derivative. If this was an A here, big matrix A has 200 rows. And so then the output of this equation will be a 200 long vector. That's not what you want, right? We need to know 9 derivative directions. And so if you just use that, you'd say probably A transpose, because when you take the transpose of A, then it's 9 rows. And so then it's like, okay, we're in good shape. That's the way I do matrix vector derivatives. Have these. I kind of guess using scalar math and then change a transpose here and there to get the right dimensions. Okay, so that's our derivative. And so here's an algorithm we could use. There's many algorithms we can use once we know this derivative, right? You can think in your head, hey, well, I know the derivative. I know I want to go downhill, or I know I can evaluate the derivative, the gradient, I guess I should be saying. And I know I want to go downhill in that 9-dimensional space. There's many ways you could do that. So one way is where you are, take the gradient, go in that gradient direction, right? Take a step in that gradient direction. Stop, take a step of a certain size. Stop, evaluate the gradient again, take another step, et cetera, et cetera. So that type of solver is called steepest descent, because each time you're evaluating gradient and going down, you're going down the steepest direction each time. There's other more efficient ways, as we'll get into. Instead of looking for the steepest route, it's actually sometimes beneficial to find the steepest route and go a little bit to the side, right? That's called conjugate gradient descent, which is generally better than steepest descent. I think everyone agrees. But we'll just do steepest descent. It's the easiest, so we'll stick with that. So here's an algorithm we can go with. So we'll set a step size. That's literally the size of my step walking down the hill. So that's probably where that term comes from a bit. How big a step are you going to take each time you try and go down the hill? So that's some number. It's up to us. If we choose too big a step size, then you can go step all the way to the valley and then sometimes over the valley. And then you're back up on the other side of the hill. So that's not great, because then you'll kind of end up oscillating back and forth. And if you select too small of a step size, then you're kind of tiptoeing baby steps down the hill. It's going to take forever, right? And so selecting the right step size is a whole art. There's actually algorithms that are all under the hood that you use to select optimal step sizes, which we'll talk about one of them later in the class. But here we'll just pick one. And then we need to select a tolerance delta. The tolerance is also really important because we're working with computers, right? Computers aren't perfect math solvers. They have precision issues. And things plateau out for a long time. Let's say the valley in your problem goes on for a really, really, really long time, right? And so you don't want to keep going forever. It's going to take forever. And so you need to set, okay, we're close enough, right? For example. So you can set up a simple while statement. This says, while we're not at the answer yet, we're not within the tolerances yet, keep going. And by keep going, I mean take where we are now with y and append to it our step size plus the gradient, right? Which means we're going down the steepest part where the gradient's pointing. Just keep doing that. And while when we're within tolerance, and then you're done. So that's what is called steepest descent, like I said. So that's method one. In this problem, I want to show there's a simpler method to solve this problem. We can solve it analytically in this simple problem. You'll see it doesn't work. I'll show you in a second. But we can try to solve it analytically, because you might be sitting there and saying, hey, there's like a parabola and we're going down the hill step by step, but I know it's a parabola. It has a bottom, right? And I know I can probably find the bottom, or I know I can find the bottom like from high school when it's a regular parabola. You just take the derivative and set it to 0. So why don't we do that, right? We can, so we will. All right, so let's go ahead and just take our gradient, right? We calculated it down there and set it to 0. Because then we know, hey, we're going to just jump to the final solution, right? Where we know it's a parabola, there's one bottom. There's one optimized point, one optimizer for the gradient 0. Okay, and so if we do that, we take our gradient. This is the equation I just showed. I took out the -2 because that doesn't matter, because it's just equal to 0, right? So it's a scalar, I can remove it. And I have A transpose times this expression, x minus A y star meaning the value of y where I know the gradient is 0, which is the optimized value, the optimizer y star, then we can solve for directly here, because this is a really nice equation. It's a linear matrix equation put into a mean squared error thing. You'll never get this lucky again in this class. Well, I guess we'll do it on the homework, but generally, the problems aren't this nice. This one is really nice. If you multiply A transpose through the brackets, you see you get an A transpose A y star. So luckily, A transpose A is a square matrix, and it's symmetric, and so it's invertible. So we have A transpose A y star. We want to move it away from y star, just like in regular scalar math. You kind of want to divide by A transpose A. Well, you can't do that in matrix algebra. I hope you guys know or remember. But you can multiply the inverse of A transpose A to either side of the equation. And so we can multiply A transpose A inverse to the left and right sides. And, A transpose A inverse times A transpose A, they cancel out, right? And so we're left with y star equals this expression on the left. A transpose A inverse times A transpose times X. So that's called a pseudo-inverse. Pseudo-inverses are your friend. You should always use them. They're great if you can. And so this pseudo-inverse, as you'll see, pseudo-inverse is so useful. It's a single key in MATLAB. It's the backslash sign. So if I want the pseudo-inverse of this equation, I would simply write A backslash X, and I would get this A transpose A inverse, A transpose multiplied by X to give me Y star. Okay, that's how common it is. It led to the formation of a single keystroke for use. But you just can calculate it explicitly too, right? We know A, we measured it. We know X, we measured it. So we just take our A measurement and our X measurement, compute the left side of this equation with them, and we get our optimal Y. So in general, this approach of taking the mathematical gradient and setting it to 0 does not work with nonlinear problems. So this problem here I drew and we set it up. It's a convex problem. So in linear optimization, you're dealing with functions that are planes, and you're trying to work within those cost functions that are formed by planes. In convex optimization, you're generally working with paraboloid-like functions. Parabolas have things that are squared, functions that are squared, have a single minimizer as well. But as soon as you take a cube, right, you get this shape that has two places where the slope could be 0. Or to the 4th power or the 5th power, right? You start getting lots of wiggles in your functions. And so then you have many, many points where the derivative can be 0. And so what you end up with when you take a derivative of some cost function in general when the problem's nonlinear, which is effectively every problem in machine learning, and you set the gradient to 0, is you get a billion trillion answers, right? Because those very complex nonlinear functions have billions of locations where the function can have a 0 derivative. And so then which one do you pick? Well, we don't know. Then you have to create another algorithm to sort through all the possible solutions, and then it becomes unwieldy, right? All right, cool. So I can do this and here I'm going to use MATLAB because I used to do some MATLAB in this course. We're not using MATLAB anymore. So apologies in advance, but the MATLAB here that I'll show, it's really similar to NumPy. So here, I made 9 spectra in MATLAB. Those are the curves on the left. Those are my 9 fluorophores. I just kind of made those up numerically. And then I made a dictionary matrix A, and I made up some percentages, Y. And then I multiplied Y into A to simulate a measurement. Right here, I'm just simulating what I might measure on a spectrometer if I put a new sample depth with unknown percentage. And so then I said, hey, I got my measured spectra. I know my dictionary matrix. Let's go ahead and compute this pseudo-inverse and multiply it into X. And that'll try to guess the best values, right? And so I can do that. And at the bottom, what I'm showing is the measurement, X in blue, and then the red curve is the result of taking my guess percentages and multiplying them into the dictionary matrix A, and they match, right? So it's like, all right, great, we solved the problem. We didn't solve the problem. All right, so if you just did this, these are the values I get for Y star. I got 0.2, so 20%, and then negative 1.1, and then negative 1.6, etc. So that is not a solution because you can't have negative fluorophores. Right? There's no such thing as negative light unless you're in the quantum world or something. So I didn't set up my problem correctly. So solution cannot have negative weights. So now I need to update my optimization approach. So this is the code I use to generate that, just so you can see it. And again, like I said, the pseudo-inverse is just this slash character. So it's pretty simple in MATLAB. In Python, NumPy, as you'll use, it's PIMD, P-I-M-D. All right, so how might I address this non-negativity constraint that I hope to apply? All right, so one way is what I just described. I can add a constraint to my solution space. So I'm going to use the same equation, minimize f of y, right? Subject to, so if you've ever read a paper and seen these kind of things, this is what optimization is all about. You're minimizing a cost function and you have some constraints on where you're searching across, what the solution is allowed to be. So I'm going to have this non-negativity constraint on my vector y, right? In the 9-dimensional space of all y vectors, I'm saying it has to lie in the quadrant of all positive values for each dimension. And so that's a convex set. If I draw a chord anywhere in that space, it won't leave that space. It's just a quadrant. And so this is a convex problem. So then I can use a convex solver. And a good convex solver to use is something called CVX in MATLAB. There's probably a CVX for Python. I actually haven't checked. There used to be, and then it disappeared, but I feel like people revived it. You might check. But there's a variety of convex solvers. They're incredibly fast. It's complicated how they work, so I won't get into that, but they're really cool. And here's how you run this convex solver. Again, it's just like 5 lines for this problem. Okay, so you do CVX begin, and we declare some variable. This is y. I don't know why I called it xc, but this is what we're trying to get. And I'm going to minimize the norm means the squared of my dictionary matrix A times this unknown that I'm trying to get minus b. B is x. I mean, I should have used different notation. Sorry. B is what I measured. And then you just write subject to the fact that all the values I'm searching over in the vector xc are non-negative. Okay. And then you end it and you hit enter, and then it just runs and gives you your values. And so that works. So here is again, in a separate simulation where I just randomly initialized the y, the measured spectra, and the guess. But they don't match exactly. You'll know, right? And so the reason why they don't match is because there's no guarantee that this is an exactly solvable problem, right? The way it's set up. Okay, and so you can just compare that we have all positive values here naturally because I applied that constraint, and the solutions are the solution for y star is wildly different than in the pseudo-inverse case. But when you actually multiply those vectors into the dictionary matrix and look at your measured spectra, they are extremely similar, right? Almost identical. So this directly shows you the challenge of solving this problem, this spectral unmixing problem. You can have wildly different fluorophore percentages, so to speak, and still get the same measurement. There's a problem with this whole setup. It's a very non-unique equation, right? In other words, I can have a measurement and it can be generated from many possible mixtures of spectra. And so just fundamentally, spectral unmixing is hard, I guess, is the moral of this story. Okay, and so there's another way we could try to solve this. This is a way that's more akin to what you might do in TensorFlow, or what we might do when we want to apply constraints to what we're solving for. You can do some mathematical manipulations to try to make sure your answer is within the space of possible answers. And so here, I'm going to introduce a dummy variable, z. And I'm going to say, no, my problem isn't minimize x minus ay. Now it's x minus az squared. right? Why am I going to do that? Well, z squared is always non-negative, right? And so if it finds a z squared that works, I know I figured out the problem. And now I don't want to figure out, or I need to figure out z to figure out z squared, but really what I'm interested in is z squared. So now this problem is not convex, right? It's nonlinear. The reason why is this is to the fourth, right? So to the fourth problem can have 3 wiggles, right? Squared can have 1 wiggle, cube can have 2. So this can have 3 derivatives in general, right? But that's true across each of the dimensions. And so then it has up to 27 wiggles, 27 places where the derivative can be 0. And so there's 27 places where it bottoms out. And so I could get stuck in any of those. But we'll give it a shot. And to solve this problem, you can use a precursor to all these TensorFlow, PyTorch things that just generally minimizes cost function, right? Which is what we're going to just rely on software to do that everyone's using for machine learning. But this one is way faster. It's called minfunc, because minfunc is compatible with MATLAB. So if you're into MATLAB and you want to minimize things, this one was written like 20 years ago and it's still excellent. And I think it's still excellent. It was supported a couple of years ago still when I checked. But you can see I am old and I've been using minfunc since 2012. So I'll go ahead and go into my 2012 version. And you just write these 3 lines, right? But the challenge with minfunc, which is what's nice about TensorFlow and everything else, is it's really fast, but you need to know the gradient. You need to tell minfunc the gradient. Before TensorFlow and PyTorch and all these auto differentiation programs, which we're going to learn about, which figure out the gradient for you, when you wanted to solve optimization problems or machine learning problems, you used to have to sit there with a piece of paper and a pen and Mathematica open and try to write. You had to write out the entire gradient, which would take like a whole page of paper. And so that wasn't that fun. But here, this one's a pretty simple gradient. So the gradient function here, down here, you can see I wrote it out. You have to tell minfunc that gradient function. It's A transpose times A times abs, the square difference, times the conjugate of that term. It's kind of complicated because there's this double squaring, right? But you can figure it out. And then you hit enter, and you get something like this. So this dummy variable method, you can see, yielded a solution that doesn't match well. Why? Because we got stuck in one of those 27 valleys. That wasn't the right valley. So if I ran this 27 times, maybe one of them would be matching. But generally, I'm going to keep hitting enter and it's not going to work, right? But I gave it a shot, right? And so this dummy variable method actually works pretty well in machine learning. So don't give up on it. That's why I presented it. It's actually sometimes not such a bad way to go. Okay, so what are some other things, just to end, last minute or two, what are some other things we can do in this framework and what we're going to do in our machine learning efforts? You can add what's called a regularizer. So regularizers help with this problem of finding solutions that don't match. What regularizers do is they kind of abstractly constrain what you're searching for to more closely follow what you might anticipate in a real world scenario. And so if you knew ahead of time, hey, generally I have kind of the same amount of each fluorophore in there, right? It's not going to be like 0 and 99% for some of them. It's mostly going to be around 10, 20% across all of them. Then you can add this term where you sum up the squared values of y and add it to your cost function, right? And so then the goal of this is going to be to jointly minimize the squared values of y. And so if y is, wildly varying, the squares of those values added up will be larger than if y is pretty homogeneous, right? Just kind of following Pythagorean's theorem picture, okay? What else can we do? Well, we don't have to use mean squared error. We can use another cost function. So here I just drew 2 bars. That means the sum of the absolute value of the differences, right? People call that an L1 regularizer, where the L1 denotes that it's kind of like to the first power. L2 is the squared difference, right? For example. So that's very simple, and that leads to wildly different solutions as well. And so you can just choose different cost functions. So not square difference, but just the absolute value difference. So all of these features we're going to play with, and yeah, they're kind of useful. So I hope this paints a picture of what we're going to do. We're going to, yeah, work within this framework going forward.